A big hurdle for electric vehicles is that batteries are heavy. This battery is roughly 50 times heavier than the gasoline required to store the same amount of energy. It's not possible to fully close that gap, but it is possible to build lighter batteries by using new electrode materials. This can help make technologies like electric trucks and airplanes more competitive. My name is Josef Rizell. In this video, I will explain how we try to solve the issues stopping the commercialization of one of the electrode materials of the future. Today, the battery market is dominated by the so-called lithium-ion batteries. One of its electrodes is made from graphite, but we get a much lighter battery if we replace it with lithium metal. But lithium metal electrodes have short lifetimes and safety problems. When you charge a lithium metal battery, lithium ions are brought to the electrode surface and turned into more lithium metal. The structures that form in this process are often bad for the battery. For instance, really long branches can grow to short-circuit the battery. If that happens, the battery can catch fire. Another problem is that lithium electrodes can store less and less energy every time they are recharged. This is linked to the formation of lithium structures with large surface areas. To improve the lifetime of lithium electrodes and make them safer, we need to control how the lithium metal grows. This is why me and many other researchers try to understand how the lithium metal grows. But it is a difficult task. Lithium structures are really small. This is an electron microscope image of the lithium grown on an electrode during charging. The width of these structures are only a tiny fraction of the width of a human hair. Another difficulty is that the lithium metal is very reactive. This piece completely changed its color after 10 seconds in air. If we take the lithium out of the battery to study how it grew, it can react and completely change. Ideally, we would like to study the lithium growth where it happens, inside the battery. That way, we can also track the growth step by step. To do this, we borrow a method from medical doctors. Computed tomography, or CT, can help doctors produce 3D images of their patients. Tumors can be precisely located without needing to do any surgery. In the same way, tomography can help us look inside our batteries without opening them. This will protect the sensitive electrode materials and help us understand how the electrode materials change when we charge and discharge the battery. With the right instrument, we can see features smaller than a micrometer. To explain how this technique works, let's imagine we couldn't see through the walls of this box. How do we figure out what the inside looks like without opening it? If we shine an X-ray beam through the side of this box, we will get some idea of what's inside. Different materials can be distinguished by how they absorb X-rays. This gives a kind of shadow of the objects on the other side of the box. But this shadow does not show things like which object is in front of the other. To get this type of information, we need to do a tomography experiment instead. Let's restrict ourselves to only looking at a single cross-sectional slice through the box, like the red plane here. In 2 dimensions, the plane will look like this. To make a tomography scan, we rotate the sample and take images when the X-rays pass through the sample from all possible angles. The images we take show the intensity of the X-ray beam after it went through the box. For each image, we know the direction of the X-rays and which part of the sample absorbed more or less X-rays. For instance, along this path, we see a low intensity, and along this one, we see a higher one. That means the 2 X-ray beams passed through different materials. But how do we find the shape of the object based on this? We have to assume that the materials absorbing the X-rays are evenly spread out along the direction where the X-rays came from. Doing this for a single image, our results look nothing like the contents of the box. But almost magically, if we make this assumption for images taken from all angles and look at the sum of these, we get back the original shape of our object. If we do this for all the planes in the entire sample, we can see what's inside our box. That's essentially what we're doing with our batteries. By looking inside our batteries using tomography, like I have explained in this video, we try to learn how to make lithium metal electrodes work better. Hopefully, research on lithium metal electrodes can enable lighter and better batteries in the electric vehicles of the future. Thanks for watching.